Hello everybody and welcome to our video on applications to physics and engineering. Now of course in this section we're just going to cover a very small sample of the kind of applications you can use integration for. But nonetheless that should help give you some idea of what type of modeling can be done with these integral systems. So we're going to talk about work, and work is based on the idea of how much force it is required to move something a certain distance. So Newton's second law of motion states that force equals mass times acceleration. And when the acceleration of an object is constant, we define the work done to move the object as W equals F times D. So in other words, force times the displacement. Now that's one of the key concepts of work, is that if you, say, move an object 10 feet forward and 5 feet back, we only look at the displacement when we talk about the distance. So the displacement in this case would be 5 feet. All right, so in the SI metric system, we use the following units: kilograms for mass, meters for displacement, seconds for time, newtons for force, and joules for work. So, of course, kilograms is our unit for mass, and kilograms times meters divided by seconds squared is our newtons, which should make sense when we take a look at our force formula here. Force is mass times acceleration. So we get the mass kilograms times the acceleration, meters per second squared. And joules is the force, the newtons, applied over a certain distance, the displacement, which is m. So the units for joules are Newton meters, but we usually just describe them as joules. Now in the US customary system, things are actually a little bit simpler because we don't separate, or we don't typically talk about mass separately from force. We usually talk about the pounds for force, which is weight, the mass under gravity, right? So we talk about pounds for force and use feet for distance. So the unit for work in that case is just the foot-pound. Okay, so an example, if a 0.25 kilogram ball is lifted 1.5 meters, the force is given by F equals mass times the force of gravity. That's 0.25 kilograms, which times 9.8 meters per second squared. So the force is 2.45 newtons, but the work done is the 2.45 newtons times the 1.5 meters traveled, which is 3.675 joules. On the other hand, if a 2-pound rock is lifted 4 feet, then work is the 2 pounds, the measure of force, times the 4 feet. So you'd get 8 foot-pounds. So the value of integration comes in when we try to extend this idea past forces with constant acceleration. So the force of gravity we generally consider to be constant. Technically, the force of gravity is actually dependent on how far away the two objects are, like the center of the Earth and a person standing on it. But of course, when you're on the surface of the Earth, it's close enough to being the same distance away. So we treat gravity as being a constant acceleration, but how do we deal with it if gravity, or if our forces, whatever they are, it doesn't have to be gravity, are not constant? So we consider an interval from x equals a to x equals b, and a force, f of x, that acts on an object moving over that interval. If f of x is continuous, then over a very small interval we can treat f as if it is a constant. So what do we mean here? I'm going to draw a little picture off to the side. So let's say you've got this force function from A to B, And maybe it looks like this. So what this is saying is that I can divide this thing up into some small intervals, and I'll just do 4 subintervals for now, just for ease. And I can create a piecewise function here that's constant over each of these little subintervals. Now, of course, I won't get exactly the right amount of work by taking these distances with the amount of force, but I can at least approximate it. So the idea here is that we partition our interval into small enough equal-sized subintervals. So delta x is the distance between the two subintervals, x sub I minus x sub I minus 1, or the distance between the two endpoints of the subinterval. And then we can approximate the force on the subintervals by the force at a sample point. So we take some point on the graph, we pretend the force is constant the whole way, and then we use that level of force times the distance to measure the work on the subinterval. So now that we have the work on that subinterval, we can express it as f of x sub I star delta x. And if we add all of that work together, we can approximate the total work from the whole interval from A to B as the sum of those forces times the distances. So of course, in the picture I've drawn here, n would be 4, but ideally you'd use a lot more partitions, a lot more subintervals, so that you get a better approximation. Well, that naturally ties into our definition of the integral. So if we want to find the work done moving an object from A to B, we want to take the limit as the number of approximations goes to infinity, and that's going to end up giving us the exact value of the work. And we know that that limit of that Riemann sum is, by definition, the integral from A to B of f of x dx. Okay, so let's tackle an example. So this is a nice simple one. A particle located a distance of x meters from the origin has a force of cosine of pi x over 3 newtons acting on it. How much work is done in moving the particle from x equals 1 to x equals 2? So since we already have a force function, then this is pretty straightforward. We know that the work is the integral from A to B, in this case 1 to 2, of our force function. So we just integrate like normally. So the antiderivative for cosine is sine. This does require a u substitution, u equals pi over 3x. And I'm going to skip that. We know we're going to end up dividing by that constant, pi over 3. And then we have to evaluate from 1 to 2. So dividing by pi over 3 can be written as times 3 over pi. And now we'll evaluate sine at 2 and 1. So we get sine of 2 pi thirds minus sine of pi thirds. That's 3 over pi times the square root of 3 over 2 minus the square root of 3 over 2, which is 0. So that seems a little bit tricky. What's going on here? Why did the amount of work that was done end up being 0? Well, if we look at the function for force we have here, for cosine, this is cosine with a period of 6. So if I draw my cosine graph, but with a period of 6, it should look like this. So what's happening? Well, when we integrate from 1 to 2, we've got some positive portion here, negative portion of force here, and they cancel each other out. So to think about this in like a real world circumstance, you know, if you are pushing a boulder up a hill, it requires force to move that boulder up the hill. But that force you're pushing up, once you get to the top of the hill and you roll down the other side, the force takes care of itself, right? You don't need any force other than the gravity pulling that thing down. So you end up having the force going in the opposite direction and it cancels out. So that's the kind of thought process you should have for that kind of problem. Now, of course, it does not mean you should expect to get zero often. Just wanted to discuss that particular kind of case here. Okay, so let's take a look at another example. The graph below represents a force function in newtons. Use the graph. Oh, I guess I should have mentioned that before. Our force was given in newtons, so our work is in joules. So you should specify your units. That was 0 joules. Here again, our force is in newtons, and we're looking at the amount of work done moving an object a distance of 10 meters. So again, we're asking for the integral of this function from 0 to 10. So all I have to do is find the area under the curve. So from 1 to 3, that's a triangle. So 1/2 the base times the height. So the area of that triangle is 3/2. And then I'll divide this up. This thing up here is a semicircle with a radius 2. So the area for here is going to be pi r squared divided by 2. The area for this rectangle is 4, and the area for this rectangle is 3. So altogether that's 7 plus 3/2 plus 4 pi over 2, which is 2 pi. And I'll just write that as 8.5 plus 2 pi. And again, we were working in Newton meters, so that's joules. Okay, moving on. So now we're going to talk about Hooke's law. We're going to do a problem on that. So Hooke's law says that the force required to maintain a spring stretched x units beyond its natural length is proportional to x, meaning f of x is a constant times x. So in this picture up here where we've labeled our resting point, the idea is that if I stretch a spring out, the distance here, x, determines how much force is required to keep it stretched. So let's take a look at this example, example 3. A spring has a natural length of 20 centimeters. If a 25 Newton force is required to keep it stretched to a length of 30 centimeters, how much work is required to stretch it from 20 to 25 centimeters? So first of all, there's a little bit of a tricky thing here, which is that everything was given in centimeters, but since we're going to need to put this in joules, we need to convert all of these to meters. So instead of 20 centimeters, this should be 0.2 meters. And then 30 centimeters is 0.3 meters, so forth and so on. But there's a second tricky part here, which is that the spring has a natural length of 20 centimeters, but that's not the distance I'm concerned with. I'm concerned with how far I'm stretching away from 20 centimeters. So we've got our spring, and its resting point is here. So one of the key things that you want to do generally for these types of problems is you want to set x equals 0 to be at the resting point. So, I draw a spring. So x equals 0 is the resting point. So we're asked to find how much work is required to stretch it from 20 to 25. That means I'm going to need to integrate, but that means I need to know what k is. So the first step to this problem is to solve for k. And they gave me some information. 25 Newton force is required to keep it stretched to a length of 30 centimeters. But a length of 30 centimeters is x equals 0.1 meters. Because I'm adding 10 centimeters to the 20 I already had, but when that spring is at 20 centimeters, I consider x to be 0. So x is 0.1. So in other words, f of 0.1, which is k times 0.1 or 1/10, should be equal to 25 newtons. So solve for k, multiply the 10 across, I get k equals 250. Now, I'm asking how much work is required to stretch from 20 to 25 centimeters. So I'm actually concerned with this point, which is 0.05 meters. So the integral that I want to take is the integral from 0 to 0.05 of kx dx, right? 250x is my function, k times x. I integrate it from 0 to 0.5, or 0.05. Okay, so that gives me 250x squared over 2, evaluated from 0 to, 0.05 is 1 over 20. 250 over 2 is 125, so this becomes 125 times 1 over 20 squared minus 0. And finally, that's 125 over 20 squared, which is 400. Now, you could absolutely leave it like that, but this can be simplified. Both of these are divisible by 25. So this would be 5 over 16. And we were in Newton meters, so our final unit is joules. Okay, so that's it for that one. Now we're going to go back to looking at, we're going to look at some more types of work problems, but ones that don't involve Hooke's law. So let's take a look at this next example. Example 4. A chain lying on the ground is 15 meters long, and its mass is 100 kilograms. How much work is required to raise one end of the chain to a height of 10 meters? Okay, so this is a pretty tricky one, and really we're going to draw like 2 pictures here to get the idea. So, well, maybe we can draw 1 picture. We'll see. I might have to draw a second one. So the idea is that you have a 15-meter long chain, and you are taking this chain and lifting one end of it straight up into the air. So the idea is what's left on the ground here, that's 5 meters. And what's been lifted is 10 meters. And we make some assumptions here, like we assume that the density of the chain is the same all the way through, and we assume that we're lifting the chain perfectly perpendicularly as we lift. But that's okay. Those are standard kinds of assumptions to make. So what I really have to think about here is the tricky part is that as you lift the chain, the more you lift it, the more weight you are lifting, right? If I lift up the first foot of the chain, the next foot I'm lifting twice as much weight. And the next foot I'm lifting 3 times as much weight as the first foot. So that means that we really need a function to describe how much force is required to lift. And we can't use those previous standard formulas that we had. In fact, instead we have to figure out how to derive a formula based on the circumstances that we're looking at. So what we're going to do is take a look at this picture, and we're going to plot a point on this chain and think about what happens to this point. So we'll call it x sub I. And we're going to imagine taking a very tiny interval on either side of that point on the chain. And so this is some little length of chain delta x. And if we choose that interval of chain small enough, then we're not adding much weight as we pull up that portion. So we can assume that the function of force is going to be really close to constant over that small interval. It's not actually going to be constant, of course, but it can be close enough to constant that it's not a problem. Okay, so what do we know? We've got a point. We're lifting that point on the chain up. And what is happening to the weight of the chain as we lift it? So let's just think about what happens on this one little segment of chain first. All right, so the weight for that segment is going to be based on the density of the chain. So in other words, I need to know how much weight does each foot, or each meter, I should say, of the chain have. So the chain is 100 kilograms total and 15 meters long. So 100 kilograms divided by 15 meters simplifies to 20/3 kilograms per meter. But I need the force, and that force is based on gravity. I need my mass per meter here, and I need to multiply that by the gravitational force, and that gravitational force is 9.8 meters per second squared. So altogether, that is, when I multiply my kilograms per meter times my meters per second squared, I end up with 65.3, repeating. Okay, so now I have to think about how much each portion lifts. That's the other complicated part here. Because the end of this chain, this very top point, had to lift the entire 10 meters up. But this x sub I only had to lift that shorter distance up. So each point on the chain isn't getting lifted as much. So what we look at how much each one gets lifted individually. So if I took this x sub I, what's the distance that it's been lifted off of the ground? Well, it's 10 minus x sub I. So that's how far I had to lift that little segment of chain up. And so, in other words, the little portion of work here that we've done lifting up one segment is 10 minus x sub I times that 65.3. And I'm going to go ahead and just leave it 65.3 and not bother putting the repeating. So then the total work is approximately, so if I lift up all of those segments of chain, the total work is approximately the sum from I equals 1 to some n of this 10 minus x sub I times 65.3. Oh yes, I'm missing one little thing. Times the delta x, that's the length of the segment. Right, so here, I maybe should have been more specific about my units before. So here I had kilograms times meters over meters per second squared. But my unit for force, that would leave me without meters, right? Which makes sense because I haven't actually looked at the length of the segment. So by multiplying this here, I get my final unit that I should have, right? My unit for work should have that meters unit in it. Okay, so now that I've got that, I can integrate this thing because this is a Riemann sum. And so if I take the limit as n goes to infinity of that, I just get the integral of those functions. So in other words, the actual work, the actual total work is the integral over the distance, which is from 0 to 10, of the 65.3 times 10 minus x dx. Pull that 65.3 out in front. Take my antiderivative. That gives me 10x minus x squared over 2. Evaluate from 0 to 10. This gives me 65.3 times 100 minus 50 minus 0. And so that's 65.3 times 50 joules, which is 3,265 joules. Okay. So that's it. Now that we've figured that one out, let's tackle another problem. So this one's also a similar type of work problem, but we're dealing with a different kind of circumstance. So in this case, we have a circular swimming pool with a diameter of 30 feet. The sides are 6 feet high and the depth of the water is 5 feet. How much work is required to pump all of the water out of the side? And we're going to need the fact that water weighs 62.5 pounds per foot cubed. So let's try to draw our circular swimming pool here. Okay, so what do we know about this pool? The radius of the pool is going to be 15 feet because the diameter is 30. And we know the water is 5 feet deep, but the whole height of the pool is 6 feet. And the idea is that you have maybe like a hose down at the bottom of the pool and you're using a pump to pull that water out and dump it over the side. So the question is how much work has to be done to get that water out. So let's first start by thinking about how to use the same line of thought developing these Riemann sums. So we've got a layer of water, right? So we divide this into like chunks of water that are delta x. Now we need to set a coordinate system here. So since any water that was at the top of the pool doesn't have to move any distance to get out of the pool, we'll set the top as x equals 0. That way we can use x to mean the distance that the water has to be pumped up to get out of the pool. So we've got some little one layer of water that's delta x sub I thick. And so some point, we'll call this point in the height of the pool x sub I. And so what first thing we need to know is how much water is in this, let's call it a sliver of the pool. So the volume for that sliver is pi r squared. So that's pi times 15 squared times delta x, the thickness, right? So this is like a small cylinder. So you get the area of the circle, and then you get times the thickness for that portion. So that means that our force is the weight So 62.5 pounds per foot cubed times the volume. So 62.5 times the pi times 225 delta x. Okay, and so let's go ahead and plug 225 and 62.5 into a calculator. So what do we get here? We get 14,062.5 times pi delta x. Okay, so now our work for each subinterval is this whole thing. What was that? 14,062.5 times pi times delta x times the distance that portion of the water had to be lifted out of the pool, which is the x sub I. So we've got our force times our distance, and now we take the sum of all of those slivers of water and now how do we get the actual work? We take the limit as n goes to infinity, and that means that the work is the integral for 14,062.5 times pi times x dx. But we do have to figure out the correct bounds here. So notice, since I set the top of the pool to be x equals 0, that means that the height of the water is x equals 1, and the bottom portion would be x equals 6. So we need to integrate this thing from 1 to 6. This gives me 14,062.5 times pi times x squared over 2, evaluated from 1 to 6. Okay, the 14,062.5 divided by 2 gives me 7,031.25 times the pi. And then we evaluate the x squared at 6 and 1. We get 36 minus 1. So that's 35. So if I multiply that by 35, I get 246,093.75 times pi foot-pounds. And if I multiply by pi, we get 773,126.3171 ... foot-pounds. Okay. Well, that's it for this video. Thank you for watching.